In the video 1, we discussed when the speed of light is the same in all reference frames, how it alters the seemingly simple concept of now, the notion of present moment, how two events happening simultaneously for one observer becomes two events happening in two different times for another observer. In this video, we'll discuss how this phenomena alters the reality of space-time. In this video, we are discussing Lorentz transformations, time dilation, and length contraction. Let's once again think about three people standing at unit distance from each other. A, B, and C. B is you. They are standing still and not moving in relation to each other. This time, the distance between each other is equal but not 1 unit. The distance is a variable called delta. When time is 0, A and B are sending light signals to B simultaneously. Here is me, the moving observer, moving at a velocity v in relation to u. And this is how I see this. This is x and this is t. This is my reference frame, and this is how I see this incident. This is trajectory of A. X equals vt. This is the trajectory of u. You are standing delta distance from the origin. So your trajectory is x equals vt plus delta. This is the trajectory of C. C is standing 2 delta distance from the origin. Therefore, the trajectory of C is x equals vt plus 2 delta. This is the trajectory of a light ray sent by A towards B. X equals t. This is the trajectory of a light ray sent by A to the other direction. X equals minus t. This is the trajectory of the light ray sent by C towards B. Since this light ray is parallel to x equals minus t, this has to be in the form of x equals minus t plus some constant. Let's call it alpha. So that light ray is x equals minus t plus alpha. Let's name these 3 points P, Q, and R. If you look at point Q, x equals vt plus delta and x equals t meets up here. So we can solve for the coordinates of Q. Okay, therefore at Q, x equals vt plus delta, equation 1, x equals t, equation 2. Let's substitute x equals t here. So x equals vx plus delta. Let's take x to one side. So x minus vx equals delta. 1 minus vx equals delta. So x equals delta over 1 minus v. So at Q, since x equals t, t is also equal to delta over 1 minus v. Now, x equals minus t plus alpha also goes through this point Q. So substituting the coordinates of Q, we can find alpha. X equals minus t plus alpha. So x is delta over 1 minus v equals minus delta over 1 minus v plus alpha. Alpha is 2 delta over 1 minus v. If you look at point R now, x equals minus t plus alpha and x equals vt plus 2 delta meets here. So we can solve for the coordinates of R. X equals vt plus 2 delta, equation 1. X equals minus t plus alpha, equation 2. Alpha is 2 delta over 1 minus v. So if you deduct equation 2 from equation 1, we can get rid of x. So 0 equals vt plus t plus 2 delta minus 2 delta over 1 minus v. So vt plus t is 1 plus v times t. So we will take these things under one denominator, 1 minus v, then 2 delta minus 2 delta v minus 2 delta. So 2 delta cancels. So minus 2 delta v over 1 minus v. To make things simple, we'll multiply everything from 1 minus v. So 0 equals 1 minus v times 1 plus v times t plus minus 2 delta v. So 1 plus v times 1 minus v is 1 minus v squared. So 1 minus v squared t minus 2 delta v is 0. So t is 2 delta v over 1 minus v squared. We can substitute this value in the equation 1 and we can solve for x. So x equals vt plus 2 delta. V times t is 2 delta v over 1 minus v squared plus 2 delta. Let's take everything under one denominator, 1 minus v squared, 2 delta v squared plus 2 delta minus 2 delta v squared. 2 delta v squared cancels and x equals 2 delta over 1 minus v squared. So at the point R, xr is 2 delta over 1 minus v squared and tr is 2 delta v over 1 minus v squared. Now the question is, what will be the trajectory of r when delta varies? Since we know the coordinates of point r, we can solve it. We can substitute delta from xr to tr. Look at this 2 delta over 1 minus v squared. This is xr. Therefore, tr equals v times xr. T equals vx. So the trajectory of r is very simple and elegant. It is a straight line. It passes through the origin because when x equals 0, t is also equal 0. Its gradient is v. Look at this t equals vx line. These two events, P and Q, are happening simultaneously for you. Any number of events happening on this line are happening at the same time for you. This is the line of simultaneity of you. One particular now, one particular present moment. Those events happening simultaneously for you are not simultaneous for me. Let's look at this person A. His trajectory x equals vt. This is his trajectory of existence. This is the line he is not moving in relation to himself. His line of existence. Now look at this line t equals vx. What does this line means to him? This is his line of simultaneity. These two lines means everything to him. His present moment and his existence. Notice how symmetric these are. X equals Vt and t equals Vx. So by the symmetry, this angle is equal to this angle. Therefore, these two lines are exactly the mirror images of each other over this light ray. This is all about this very important line of simultaneity, the now line or the present moment. Now imagine these two people are holding a tape. This is you. According to you, the length of the tape is 1 unit. According to me, who is moving in relation to you, what is the length of this tape? Let's draw a space-time diagram for this. This is your frame of reference. This is your x-axis and your t-axis. This is the trajectory of A. X equals 0. This is the trajectory of U. X equals 1. And this is what you mean by the length of the tape when t is equal to 0. What do I mean by the length of the tape? This is my trajectory of existence, x equals vt. And this is my line of now, t equals vx. What I mean by the length of the tape is the distance between its two ends in my present moment. A distance measured simultaneously in my frame of reference. So according to me, this is one end of the tape and this is the other end of the tape. So this is the length of the tape according to me. Notice according to you, this is a measurement of two ends of the tape in two different times. So what you mean by the length of the tape will not agree with what I mean by the length of the tape. The problem is how to calculate this distance. Well, you might think this is simple. This length is 1 and this is t equals Vx. Therefore, this is V. So by Pythagoras, this length is square root of 1 squared plus V squared. You cannot calculate it that way. Ordinary notions of space geometry does not work here. This is not space. This is space-time. Pythagoras does not work here. To transfer a particular point in your coordinate system to my coordinate system, we need to work out a coordinate transferring system. This is your coordinate system, x and t. And this is my coordinate system, x bar and t bar. This is t bar equals 0 and t equals Vx. Let's write it as t minus Vx equals 0. This is x bar equals 0 and x equals Vt. Let's write this also as x minus Vt equals 0. If these two coordinate systems are to be related to each other according to the way we want them to be related, there are three things to be satisfied. The first one is when t bar equals 0, we want t minus Vx also to be equal to 0. This is because we want them to be one line, not two lines. So t bar equals t minus Vx equals 0. But t bar should not necessarily be equal to t minus Vx. There can be a some factor f. So t bar equals t minus Vx times f factor equals 0. This is equation 1. Similarly, when x bar equals 0, we want x minus Vt also to be equal to 0. In other words, we want x bar equals 0 and x minus Vt equals 0 to be the same line. Once again, this also can be vary from a factor. Let's call that factor g. So x bar equals x minus Vt times g equals 0. This is equation 2. The second relationship between these two coordinate systems is the speed of light is the same in both coordinate systems. That is, when x equals t, we want x bar also to be equal to t bar. Or in other words, x equals t and x bar equals t bar needs to be one line. So x divided by t equals x bar divided by t bar equals 1. Let's divide our equation 1 from equation 2. So 1 divided by 2, that is t bar divided by x bar equals t minus Vx times f divided by x minus Vt times g. When x bar equals t bar and x equals t, let's substitute t with x here. So x bar divided by x bar equals x minus Vx f divided by x minus Vx divided by g. So this shows f divided by g equals 1. In other words, f has to be equal to g. The third relationship is there is no absolute velocity. According to you, I am moving, and according to me, you are moving. They're exactly the same way. So when t bar equals f times t minus vx, it should be also true that t equals f times t bar minus vx bar. But there is a difference. In relation to you, I am moving to north, this direction. In relation to me, you are moving to south, this direction. Therefore, in relation to me, v becomes minus v. So this v has to be minus v. So t equals f times t bar plus vx bar, and x equals f times x bar plus vt bar. This is sufficient to calculate the factor f. Let's substitute x bar and t bar from equation 1 and 2 to equation 3. T bar equals t minus vx times f, equation 1, and x bar equals x minus vt times f, equation 2. So t equals t bar plus vx bar f. So we'll substitute for t bar and x bar. So t times bracket t minus vx times f plus v times x bar is x minus vt times f, the whole thing times f once again. So t equals t minus vx plus vx minus v squared t, whole thing times f squared. So v minus x cancels off. So t equals 1 minus v squared f squared times t. So t cancels off. F squared is 1 over 1 minus v squared. In other words, f equals 1 over 1 minus v squared. So these are our two equations. T bar equals t minus vx over 1 minus v squared, and x bar equals x minus vt over 1 minus v squared. These are the Lorentz transformations. So let's get back to our original question, the length of the tape. Let's call this point P. At P, t bar equals 0 and x equals 1. Let's substitute these to this equation. T bar equals t minus vx over 1 minus v squared. So t bar is 0. So 0 equals t minus v times 1. So that shows t equals v. So let's substitute t equals v to the second equation. X bar equals x minus vt over 1 minus v squared. So x bar equals 1 minus v times v squared over 1 minus v squared. So x bar is square root of 1 minus v squared. So this length is shorter than this length. So to a moving observer, length in a non-moving reference frame is shorter. This is the length contraction. Let's look at what happens to the time when observer is moving. This is x, t equals 0. And this is t, x equals 0. This is your frame of reference. And this is me, x equals vt. I am carrying a clock with me. Let's say at the origin, your clock and my clock read t equals 0. The question is, when your clock reads 1, what is the time in my clock? So at this point P here, t equals 1 and x bar equals 0. Let's apply to Lorentz transformations. X bar equals x minus vt over 1 minus v squared. X bar equals 0. Then x minus v times t is 1 over 1 minus v squared. So this shows x is v. So let's apply this to t bar. T bar equals t minus vx over 1 minus v squared. T is 1 minus v times x is v squared. So t bar is equal to square root of 1 minus v squared. So in your frame of reference, my clock is running slower. This is the time dilation. Now, the question comes to your mind is, how real is this phenomena? Is it just my clock looks running slower to you? Or does it mean my clock is really slowed down? Is it reality or is it illusion? Let's do a thought experiment on this. Let's think you and I are twin brothers. This is you and this is me. I am moving passing you at a velocity v. And this is a wall. Let's draw a space-time diagram for this. This is your reference frame, x and t. This is me, x equals vt. When your clock reads t naught to you, I am going to hit against the wall. I hit in a totally elastic manner, and now I am moving towards you at the same velocity v. The question is, when I reach home, what is my age? So this is t naught. This is my trajectory after hitting on the wall. And this is me reaching home. When t equals t naught, what is t bar? Along this line, x bar equals 0. And when t equals t naught, let's find what t bar is. X bar is x minus vt over 1 minus v squared. When x bar is 0, x minus vt naught is 0. So x is v times t naught. T bar is t minus vx over 1 minus v squared. When t is t naught minus v times v t naught, that is 6. So T naught minus V squared T naught over 1 minus V squared. 1 minus V squared T naught over 1 minus V squared. So T bar is T naught times square root of 1 minus V squared. By symmetry, your time when I reach home is 2 T naught and my time is 2 times T naught over 1 minus V squared. To get a feel of it, let's think my velocity is 16 over 25 times the speed of light. And according to you, I came home after 100 years. So when I come back home, you are very old. The question is, what is my age? So let's substitute to T naught over 1 minus V squared. 100 times square root of 1 minus 16 over 25. 100 times square root of 9 over 25. 100 times 3 over 5 equals 60 years. So by the time I come back home, I am a 60-year-old still young person and you are 100 years old. It is not an illusion. It is the reality. When I move passing you at velocity v, my time really passes slower in relation to you. And your time really passes slower in relation to me. And that is the nature of reality. In next video, we look at the concept of proper time. Subscribe to this video channel because this is going to be a complete comprehensive course on special theory of relativity and nature of time. You can download this lecture note from the link given below.